Welcome. This is a little video about describing Project 2 for CPE 329, our function generator project. In this project, it's actually a quite difficult project in the sense that you have to learn how to use a microcontroller to create timing. So you'll use a timer to generate interrupts, and you'll need to spit out analog waveforms, and you'll use a DAC, which has an SPI interface, and so you'll need to do all of those things. And fortunately, you've already probably worked on the timer and interrupt, as well as the SPI and DAC tutorials. So I guess as educators like to call it, you have been scaffolded. The function generator has several specifications. The DAC that you use needs to have a minimum 8-bit resolution and an SPI interface. The function generator must be able to create a square wave with a variable duty cycle, a sine wave waveform, and a sawtooth waveform. So your waveform should be biased, DC biased around VDD over 2. It depends if you're using a 3.3 volt or 5 volt system, that may change. The waveforms all need to have adjustable frequencies from 100, 200, 300, 400, and 500 hertz. To get full credit, you need to get less than 2.5% error. So what is that? That's 10 for the 500 hertz, and plus or minus 10 hertz. So on power up, the function generator should display a 100 hertz square wave. To switch the wave between the waveforms, you're going to press a button, and it goes from sine wave to sawtooth to square wave, then back around to sine wave, square wave, sine wave, sawtooth, square wave, back around and around. You should also have another button that changes the frequency of the waveforms, so that cycles from 100 up to 500 and back around again. Then the third button should be there to change the duty cycle. So originally your square wave is going to start off at 50%, then it'll go up to 60, 70, 80, 90, 100, which will be always high. Then back down to 0 afterwards. And then back up to 10%, 20%. And in general, you must use the timer to generate all of your timing events. I'll describe that a little bit more. A couple of tips with this: do try to start simple. Start with developing the square wave, because it's easiest with the timer, and just start getting that planned. You want to probably plan how many points you want to write to the DAC per period for each of the waveforms, and it's probably best if you keep that number constant, and I'll talk a little bit more about that in just a minute. It's really tempting to use the sine function in C programming, but you don't want to use that in runtime. What do I mean by that? I mean, in your while of one loop, where you're actually spitting out points, you're not going to want to calculate sine values. The reason is because the sine function in the math.h header file uses double precision floating point, which has to be emulated on our tiny fixed point microcontroller. So it may take you thousands of cycles, tens of thousands of cycles to generate a single sine wave point. And if you're trying to spin out, let's say, 20 samples in less than 0.01 seconds, you'll need to do those many cycles every point, and you may miss your timing constraint. So to get around this, one common microcontroller trick is to use pre-computed values stored in a lookup table. So for instance, your sine wave itself could be values that are pre-computed and stored into a memory array. And a memory array kind of looks like this. Let's say sin array, let's say we had 20 points in there, would be equal to this, and I don't know, what's the values of the sine wave, 1, 5, these are obviously fake values, right? But it'd be, and that's how you start using an array. And then you can index through the array with either a pointer, or just to get like the third element of the array, you can do something like sine underscore array of I, where I could be, you could keep incrementing I until it hits the end of the array. And also with this project, finally, expect there'll be several hours of fine-tuning your function generator to meet specification. Um, you can do all the calculation in the world with the timers, but ultimately you'll have to probably tweak your timer values. So let's talk a little bit about how to generate the square wave. So here I've drawn one period at 100 hertz or 0.01 seconds, and I have three different waveforms. I have a square wave here, I guess a sawtooth wave, right? We go down and then back up again. And here's my crappy sine wave. It's actually just two half circles. And so the first idea is, well, okay, let's say I had like 10 points per period. So I'm gonna, each of these lines here is gonna be another point, 1/10 of 0.01 seconds. And the reason I'm copying them here is I'm gonna see, this one's not snapping. There, I don't know why there's so many of these. Okay, so for all of my waveforms, I can compute where these intersections are here. So this and if we assume that this value here, let's say for the sine wave up here, this is going to, for our 12-bit DAC, we're going to vary between 0 down here. So in hexadecimal, or in decimal, it'll be 0. And up here, this will be, since if it's a 12-bit DAC, it'll be 4095 is the largest 12-bit number. And this will correspond to VDD, and this will be 0 here. And so all these values here are going to be in between 0 and 4095. You should have understood this from the DAC assignment, that it's a linear distribution in this range. And so all you have to do here is maybe come up, this would be like my sine array, and I guess I'd have, in this particular one, I have 10 points in there, and I can populate those values here. That I don't know, if it starts off in the middle here at 50%, I guess it'd be 2048, then something else, something larger than 2048. I'll just guess 2700, etc. All right, so that would be my sine array here. Likewise with the sawtooth, it's just a line, so you could probably figure that one out. Again, starting at 0 volts, or at 0 or ground at 0 for the ADC up to 4095. So each of these things is going to be another 409 greater. So this would be 0.0, this would be 0, 4090, 409, 818, so on and so forth. And for the square wave, it's really simple. It's 0, 0, 0, 0, 0. 4095, 4095, 4095, etc. And the reason I kind of recommend this way, the square wave only needs 2 points, but here if you have 5 points low, 5 points high, it doesn't matter what waveform you're actually displaying. You just the only difference is you go into a lookup table and spit out a different number. And then also this way, it's pretty trivial to add a different type of waveform. So that's my recommendation for project 2. Do be aware, of course, this project is probably the longest project of the quarter, with the possible exception of your final project. Thank you.